Failures of construction equipment and accessories, metallurgical root cause analysis, investigating material defects causing equipment breakdowns. Introduction, overview of failure mechanisms. Construction equipment and accessories are subjected to extreme working conditions, making them vulnerable to various types of failures. Metallurgical root cause analysis plays a critical role in identifying why these failures occur and how they can be prevented. This process involves examining the material properties, manufacturing processes, and service conditions to pinpoint the exact cause of failure. Understanding these factors is essential for improving reliability, reducing downtime, and ensuring safety in construction operations. The introduction sets the stage by explaining the importance of metallurgical analysis in failure investigations, highlighting its relevance in preventing costly breakdowns and accidents. It also emphasizes the multidisciplinary nature of the analysis, which combines material science, engineering principles, and practical field observations to deliver actionable insights. Failures in construction equipment can be broadly categorized into four main types: those caused by improper material selection, manufacturing or fabrication defects, service abuses, and inadequate maintenance or inspection. Each category has distinct characteristics and requires specific analytical techniques to diagnose. Improper material selection often leads to premature wear or catastrophic failure under stress. Manufacturing defects such as welding cracks or porosity compromise structural integrity. Service abuses, including overloading and exposure to corrosive environments, accelerate degradation. Finally, poor maintenance practices allow minor issues to escalate into major failures. This overview provides a framework for understanding the subsequent detailed discussions on each failure type and their metallurgical implications. Failure due to improper material, failure due to manufacturing and fabrication defects. Improper material selection is a common cause of equipment failure. When materials lack the necessary mechanical properties, such as tensile strength, toughness, or corrosion resistance, they cannot withstand operational stresses. For example, using low-grade steel in high-load components can lead to fatigue cracks or brittle fracture. Metallurgical analysis in such cases involves examining the chemical composition and microstructure of the failed part to verify compliance with specifications. Techniques like optical microscopy and hardness testing help identify deviations from expected properties. Real-world examples include bucket teeth fracturing due to inadequate hardness or hydraulic cylinder rods corroding because of poor alloy choice. Preventing such failures requires rigorous material selection protocols and adherence to industry standards. Manufacturing and fabrication defects significantly compromise the structural integrity of construction equipment. Common issues include welding cracks, porosity, slag inclusions, and improper heat treatment. These defects often originate from inadequate process control or poor workmanship. Metallurgical root cause analysis focuses on identifying these flaws through non-destructive testing, NDT, methods such as ultrasonic or radiographic inspection, followed by microscopic examination of fracture surfaces. For instance, a weld crack in an excavator arm can propagate under cyclic loading, leading to catastrophic failure. Preventive measures include implementing strict quality control during fabrication, proper welder training, and adherence to welding standards. Understanding these defects is crucial for improving manufacturing reliability and reducing failure rates. Failure due to service abuses, failure due to improper maintenance and inspection. Service abuses occur when equipment is operated beyond its design limits or exposed to harsh environmental conditions. Overloading, improper usage, and neglecting operational guidelines are common examples. These abuses lead to accelerated wear, fatigue, and corrosion. Metallurgical evidence of service abuse includes deformation marks, fatigue striations, and corrosion pits observed under scanning electron microscopy, SEM. Stress-strain analysis often reveals overstressing beyond yield limits. Preventing such failures requires operator training, strict adherence to load specifications, and regular monitoring of service conditions. By correlating metallurgical findings with operational history, engineers can identify patterns of misuse and implement corrective measures to extend equipment life. Improper maintenance and lack of timely inspection are major contributors to equipment failure. Issues such as inadequate lubrication, delayed replacement of worn parts, and ignoring early warning signs can escalate into severe damage. Metallurgical analysis often reveals wear patterns, surface scoring, and oxidation indicative of poor maintenance. For example, bearing failures due to lubricant contamination or gear tooth breakage from misalignment are common scenarios. Implementing preventive maintenance schedules, using condition monitoring tools, and conducting regular inspections are essential strategies to mitigate these risks. A proactive approach not only reduces downtime but also enhances safety and operational efficiency. Root cause analysis workflow, preventive measures and conclusions. The root cause analysis workflow for metallurgical failures involves several systematic steps: initial failure observation, collection of background data, non-destructive testing, sample preparation, microscopic examination, and chemical analysis. Each step provides critical insights into the failure mechanism. For instance, fractography helps identify fatigue versus brittle fracture, while hardness testing confirms material properties. Flowcharts are often used to visualize this process, ensuring a structured approach that minimizes oversight. This workflow enables engineers to trace failures back to their origin, whether it is material-related, manufacturing-induced, or service-driven, and develop targeted corrective actions. Preventing failures in construction equipment requires a multi-pronged strategy. Key measures include selecting appropriate materials based on operational requirements, enforcing stringent quality control during manufacturing, and implementing robust maintenance programs. Operator training and adherence to service guidelines further reduce the risk of misuse. Metallurgical root cause analysis not only helps in diagnosing failures but also provides valuable feedback for design improvements and process optimization. In conclusion, integrating metallurgical insights into equipment lifecycle management enhances reliability, safety, and cost-effectiveness, making it an indispensable tool for the construction industry.